Alright, so let's start by talking about what this P versus NP problem actually is. It is one of the most well-known open questions in computer science, and the question it asks is simple to state, but extremely hard to answer. If a solution to a problem can be checked quickly, can it also be found quickly? Now, when we say quickly, we are talking about polynomial time. That's what defines the class P, and NP stands for non-deterministic polynomial time, where the solution can be verified in polynomial time, but we don't know if it can be found in polynomial time as well. The big unknown is whether P equals NP or not. And let's take a look at this complexity chart to see why this matters. On the horizontal axis here, we have got the size of the problem, and you can see 10, 15, 20, okay, and that's okay, like the number of variables or items or nodes depending on the problem. And on vertical axis we are showing how long it takes to solve that problem. It gets bigger. And now we draw two curves here. What are they? One for polynomial time and one for exponential time. The green one is something like n square here. This is what we usually consider tractable. The red curve here grows like 2n squared, and you can see how it shows up as n increases. And let's stop here for a second. At n equals 10, the polynomial function gives us 100. So that's 100 operations, which is not a big deal. But for the exponential function, we have already at over 1000, and that's 1024. And if you keep going past that, the numbers get out of hand very quickly. So that's the danger with exponential growth. It doesn't take long before it becomes impossible to compute in practice. So why are we looking at this? By the way, let me show you, and here you can see, and let's start at 10 again. So well, in AI and in a lot of optimization problems, we are constantly running into search spaces that grow exponentially. That means even if we know what a good solution looks like, finding it might be way too expensive, and that's where this P versus NP question becomes relevant. And let's talk about what P and NP actually include. Problems in P are the ones we know how to solve efficiently. Polynomial time like O(n square or O(n power), and sorting algorithms like merge sort or quick sort are in this group. So are graph algorithms like BFS and DFS. Even matrix multiplication and linear programming fall under this category. We have null algorithms that solve them efficiently. On the other hand, NP problems are the ones where we can verify a given solution quickly, but we don't know how to find it quickly. Boolean satisfiability is the classic example, and that's the SAT problem here. Then there is the traveling salesman problem, graph coloring, and subset sum. These are all problems where checking an answer is easy, but getting that answer in the first place is a different story. So this takes us to the main question. Is P equal to NP? In other words, is there a first algorithm out there for all the problems we can verify quickly? Most people think the answer is no, but nobody has been able to prove it either way. And here's the diagram, so you can see the relationship. P is this green region, problems we can solve efficiently, and P is this bigger region, problems where we can verify a solution efficiently. And then there is a smaller set inside NP called NP complete. Okay. These are the hardest problems in NP, and if you could solve even one of them in polynomial time, all NP problems would be solvable in polynomial time too. That's why people care about them so much. So, what does all this mean for AI? Well, a lot of AI problems are NP hard. That includes tasks like optimal planning, constraint satisfaction, learning the structure of Bayesian networks, and selecting features in a model. These are problems where finding the optimal solution is not feasible at a large scale unless P equals NP, which we are assuming is not the case. Because of that, AI researchers and engineers don't try to solve these problems exactly. Instead, they use approximation algorithms. The idea is to find a solution that's close enough to the best one, something that works well enough even if it is not perfect. And more often than not, this is good enough in practice. There are a few different ways AI deals with NP hard problems. One of them is to use approximation algorithms like I just mentioned. Another is to bring in a heuristic. These are rules of thumb that help guide the search in a smarter way based on the domain. And then there is learning from experience. We use machine learning to recognize patterns in problems we have seen before and apply that knowledge to new problems. And parallel processing also helps. If you have got multiple processors running at the same time, you can try out different solutions in parallel, which speeds things up. And in more experimental areas, there is quantum computing, and some quantum algorithms might be able to speed up search in specific cases, though that's still very much in early stages. So overall, the P versus NP question is not a just theoretical puzzle. It is one of those questions that sits at the core of what's possible, especially in AI, where we are constantly working with problems that are hard to solve. And until we know the answer, we have to keep relying on smart approximations, heuristics, and all the tools we have got to handle these problems in a reasonable amount of time.